I will be talking about the monopoles. So the topic of my talk was monopole searches in Nadal or Moidal. So Albert Rock told us that how to pronounce this experiment is Nadal. So you will and the O is silent. Nadal experiment. So Albert Rock has talked about the experimental aspect of these monopole searches. So that's why I decided to change a little bit the topic of my talk. So I will be rather talking about the theoretical insight or motivation behind these searches. So what does it imply if we have a monopole? So I will be talking about that thing. So and I don't know if so what's the motivation behind monopoles? So we will be talking about this motivation at classical level. So I will be talking about classical electrodynamics. So there are symmetries which will assist that there should be a monopole. Then we will go to quantum level. We will see that there are how Clark has related the monopole existence and the charge quantization. So,
Sir, as long as you were using the classical model to explain, I had a confusion. Can you address that? Or
yeah, we will explain this classical and charge quantization in detail. And then we will go to somewhat more advanced level.
Sir, it was a very brief question. Multiple expansion जब हम करते हैं तो हमारे पास जो है वो ऑटोमेटिकली दिखाता है उसके अंदर के मोनोपोल्स नहीं एग्जिस्ट करने चाहिए. सो ये बात हम कैसे जो है जी सर, तो वो तो उसमें तो आप कह रहे हैं, लेकिन क्लासिकल थ्योरी में कहती है कि आने चाहिए हमारे पास मोनोपोल्स.
क्लासिकल थ्योरी सजेस्ट करती है कि वो किस तरह के बताऊं.
ओके सर, थैंक यू.
दिस इज द ओल्डर वर्जन मैक्सवेल इक्वेशन. वी आर नॉट फैमिलियर with this form of Maxwell equations. Today, we use divergence and curl notation. So this is a modern version of Maxwell equations. We have divergence of E over epsilon r. This is the electric charge density. Then we have curl of E. Divergence of B is 0 because we don't see any magnetic monopoles. We do see magnetic electric monopoles. Then we have this curl of P equation, and this is the electric current density. In free space, divergence of the source, there are no charges around, so divergence P is 0, and this curl of P is related to the time derivative of P. Divergence of P is already 0, and we have this. So it's an exercise. There will be three exercises for you. So if you how can you get this equation from Maxwell equation? So you can take the curl of this equation. So curl of P, you will get divergence of P, which is 0, and then curl of P, you can use this equation, and then you can get this equation. And for electric field, and if you take the curl of E, if you take the curl of this equation and use other equation, you can get the same equation from magnetic field. So this equation is telling us that light is an electromagnetic wave which is moving with the speed of light. Next, the covariant form of Maxwell equation. Maxwell's equations and electrodynamics is consistent with relativity. So you can transform this equation into a form which is very much consistent with relativity. That's the covariant form. So this is the covariant form. Here you have this antisymmetric tensor F mu, which is called electromagnetic field tensor, and you have electric field 3 components and the magnetic field 3 components. This is antisymmetric tensor which has 6 independent components: electric field and magnetic field. And here this derivative, you have time derivative and space derivative, is the 4 derivative, and here you have 4 current, you have charge density and charge current. So you can write down the Maxwell equation with sources into this form. So there are these four forces. The free index mu carries four values, four, and these are also four equations. This is a scalar equation and this is a vector equation. So we will count it as three. So four equations. What about the source free Maxwell equations? So there is a electromagnetic duality. If you consider Maxwell equation in free space, you can see if you replace in these two equations E by B and B by minus E, these are the duality transformation. You get divergence of B from divergence of B, and you get curl of B from curl of B, and you can rewrite this equation as this. So these are the other four equations. So you can get other four equations, which are actually the source free equations, from the first four equations via the duality transformations. So in general, these duality transformations are described by this. So this is a rotation, kind of rotation by parameter alpha. So as an exercise, you guys will show that if you transform electric field by this general duality transformation, these Maxwell equations are invariant in free space without sources. So this gives you a hint how we can write the covariant form of source free Maxwell equation. So we will use duality transformation. We will replace E by B and B by minus E. So if you do that, you get a dual tensor F tilde. Instead of E we have B, and in place of E we have E. So we get this equation. So, and there is no source. This is the source free four equations. We have four values of F mu nu tilde equal to 0. And now you can, as an exercise, you can see, you can also write down this dual tensor F mu nu in terms of field tensor by this Levy beta symbol. This is a totally antisymmetric object, and it carries, the 0, 1, 2, 3 value is plus 1. So next we move on to Lorentz-Post law. So we know the Lorentz-Post law is equal to Q E plus P cross P. So if you make this transformation to this Lorentz-Post law, you place E by B and B by E, you get a dual kind of force. You can see it's charge times B and charge times P cross E. So you can add in Lorentz-Post law another term with magnetic charge. This first part, now we will add subscripts. This one is electric charge and this is magnetic charge. From this we can write down such that, and that this Lorentz force, generalized Lorentz force law is invariant under these generalized duality transformation, where you replace electric charge with the magnetic charge like this, and the magnetic charge with the electric charge. If you do that, these two terms will transform into each other, and the Lorentz-Post law will remain invariant. So with charges, so same is the case if you consider the Maxwell equation with sources. You can make it consistent like this. We have divergence rho E over epsilon r. This one, the old with electric charges and currents, and this one now you can have magnetic charge density or magnetic current. And from these two equations, as an exercise, you can see that you can derive the permeability equation, which is a statement of charge conservation. Same is the case with this, and this equation you can write down in covariant form like this. So there is a duality transformation of Maxwell, of a generalized Maxwell equation, where F mu nu is replaced by F tilde mu nu, and F tilde mu is replaced by minus, and the currents are transformed like this. So this is the most symmetric Maxwell equation. If you don't have sources, then the symmetry you have seen, there is a symmetry between E and B. But if you have sources, then you can make your Maxwell equation symmetric under this transformation, and it implies that there should be a magnetic charge. Then your Maxwell equation will look symmetric. So this is just a symmetry argument. you want to see at the fundamental level your large should be symmetric. Why there is no magnetic pole? You have electric pole. So this is a kind of mathematical statement. So at classical level, you expect that there should be magnetic monopole. When you add the quantum mechanics into the story, so you will see there is an interesting twist with the presence of magnetic monopole. So this exercise, you can check your generalized mathematical equation under the generalized duality transformation. So next, Dirac monopole and charge quantization. So Dirac assumed if there exists a magnetic charge. Okay. So magnetic monopole, assume that a magnetic monopole with charge Q M exists. Let's say put it at the origin. Then you can calculate its magnetic field. So just like electric charge. So here you have 1 over 4 by epsilon naught. Now 1 over epsilon naught will be replaced by mu naught, and everything looks same. And now consider an electric charge which is moving in the magnetic field of this magnetic monopole. So you know the Lorentz force F R double dot equals to Q E V cross P. Now let's consider the rate of change of its angular momentum. Angular momentum is R cross P. Momentum is mv. We will take the time derivative. So time derivative R dot, it will be 0 R V cross V 0, and then time derivative of this thing, so it will be R plus M R double dot. You can put this equation here and you get this thing, and then you put the formula of magnetic field from here, so you get this thing. And then as a last step, which I left as an exercise, if you take the derivative of this R unit vector, you get this thing. R unit vector, write R unit vector over its magnitude and take the time derivative, so you will get this step. So time derivative of angular momentum equals to time derivative of something. So you can bring these two pieces together. So the time derivative of something is 0, and this something we know is the something angular momentum. So this suggests that this is the total angular momentum. You have this part and this part and this part, this part. I mean, this is some way related to the this angular momentum is coming from the fields, electromagnetic fields, and you can show it as an exercise. We know the angular momentum contained in this electric field that carries energy. It carries energy, it carries momentum. If it carries momentum, it carries angular momentum. This is the pointing vector tells you where the energy is moving. So this step you will do as an exercise, and you can show that this part is actually coming from the angular momentum of electromagnetic radiation. So this we get total angular momentum. Now we have the quantum mechanics. We know angular momentum is quantized. For quantization, angular momentum is quantized. So this electromagnetic is quantized and is integer. So then you can get this piece is also quantized, is n h by 2. So this is very simple derivation. Very simple derivation. So if you have a magnetic monopoles, it implies charge quantization. So n is an integer, and you can write down this charge, whatever value is qm. So this electric charge will be integer times of some quantity. So that means quantization. You see the charges in terms of integer. 1 E charge or 2 E charge or minus 2 E charge. You don't see a particle with pi E charge or something.
So fractional charge भी तो होता है.
Whatever fraction you have 1 over 3, the smallest fraction will play the role of the fundamental charge, and then we have integers. Okay. So now I will again derive the same thing, but in a bit rigorous way. For that, I need to introduce this dark string. So you have magnetic field. You can take its divergence. You know the divergence of D will be some charge density. It is a magnetic charge density delta function. And if you integrate this equation over the 3 volumes, so using divergence theorem, you can convert this integral into surface integral, closed surface, which is enclosing the volume, which contains that charge, and here you have this charge. Q. This is the magnetic flux, the definition of magnetic flux, which depend on the magnetic charge at the center. Now, if R is not equal to 0, we are not talking about the origin, then divergence of B should be 0. Divergence of B should be 0. Only at R equal to 0 you have some singularity because there is a point charge there. So divergence of B is 0 elsewhere, then you can write down B as a curl of A. B as a curl of A. Okay, if you can write down B as a curl of A, so there is an important point which I want to stress here, then this A will not be well behaved all over the space. It will contain singularity, and this we can see from here. Now consider an open surface, B dot ds open surface. So this, consider this surface which is like the balloon, and it has an opening at the north pole. So this surface as open surface, you can convert this thing into A dot dl, because B is curl of A, the Stokes theorem here, and then A dot dl, and now try to close that opening. As you close this opening, it will become a closed surface, and for closed surface we know there is a magnetic charge inside. So as C goes to 0, this opening closes and this S open becomes a S close. This will be 0 as long as A is well behaved. As long as, if it has a singularity, then you cannot draw this conclusion. So which means, because we know that this should not be 0, because there is a magnetic charge enclosed in this loop. So this means that Gauss's law implies that A should be singular. As an example, you can write down many A's, because A is not a unique thing. So one solution of this problem could be this. So this N representing the north, and Y is a north, and there will be a south. So this is a solution. If you take the curl, you will get the magnetic field from here, and you can see that at theta equal to 0, we have this 2 divided by 0. So this is infinite. One singularity is already at R equal to 0 due to that magnetic dipole. Another singularity is coming at theta equal to 0. Theta equal to 0 means positive z axis. So there is a singularity. A is singular at positive z axis, and you are trying to close it. So you can understand it will not go to 0 because A is singular. This is an example. So positive z axis A is singular. You can also, in principle, you can close this surface at any direction. See, any direction. But I am simplifying the situation. I have picked the z axis. So second, you can also have another solution, south, A south, and there you can see at theta equal to 0, this is a 0 by 0 form, it's finite at theta equal to 0, but at theta equals to pi, cos of pi is -1, so numerator is okay and denominator is 0. So it has a singularity at negative z axis. So you can write down, you can calculate the curl of this thing, you will get this thing, and you also have something.
इसमें cos थीटा नीचे होगा ना, ऊपर sin थीटा होगा. अगर पाई पे सिंगुलैरिटी हमें चाहिए तो cos थीटा डिनोमिनेटर में नहीं होगा.
नहीं, तो एक cos जो पाई है वो -1 हो जाएगा, तो ये ऊपर 2 हो जाएगा, न्यूमरेटर फाइनाइट हो जाएगा, और sin ऑफ पाई जो है ठीक है. कुछ यूनिक सॉल्यूशन है, बहुत सारे इस तरह के, कुछ इसके इनवर्स वाले सॉल्यूशन.
उसमें लिखा है कि as is singular at theta is equal to pi.
हाँ, as is singular at theta equals to pi, तो सही था.
ये तो थीटा इज इक्वल टू थीटा पाई पे तो ये सिंगुलर नहीं होगा, cos होना चाहिए.
जी एक्सिस का मैंने गलत लिख दिया, नेगेटिव जी एक्सिस का मेरा करता है, क्या लिखा है पहली बार. हाँ, ये टाइप है, ठीक है. तो
लेकिन फॉर्मूले में अगर हम पाई डालें तो फिर तो फाइनाइट ही आ रहा है ना. अच्छा साई पाई, हाँ पाई पे तो 0 है. ठीक मैं पाई बाय 2 समझ गया. ठीक.
So you can write down this term, and this represents that singularity, and if you take the curl of AN, you get this magnetic field when theta is not equal to 0, and you take the curl of AS, you get the magnetic field, same magnetic field which is produced by magnetic charge, except you don't need to include theta equals to pi. So in this two way you can construct this thing. So now you have two vector potential which are describing the same physics, you can say, but these two are different. So you can make a gauge transformation. You can connect these two gates through a gauge transformation because these vector potentials are connected by gauge transformation. So which we can see from here, the curl of the difference of these two is 0. If curl of some quantity is 0, you can write down that quantity as a gradient of this type, and this is that gauge function, that function which connects the one vector potential to another, which connects the south vector potential to the north. So we can take the difference, you will see this cos theta factor will vanish and you will have 1 over sine, 2 over sine theta thing, and it will be 5. So you can calculate chi. So and I have calculated this chi with a special case just to tell you some more simple situations. Theta equals to pi by 2. So we are considering equator. So your surface is like equator for north and for south also. So theta is this, pi is this. Now consider V dot sigma. So now consider a closed surface V dot sigma and decompose that closed surface into two, the northern hemisphere and southern hemisphere. So this is the southern, this is the northern, and now you can calculate because B's you can write down as curl of A in these regions, curl of A, south, north, and now you can use Stokes theorem, and this is the open surface. Okay, this is the type of open surface, and you can use this Stokes theorem. You have the boundary of this equator which is running in opposite direction for above. I mean the northern hemisphere. If it is like this, then for the southern hemisphere the sense of rotation will be opposite. So there is a minus sign. So now you can, and this E means equator. So at equator you combine these two things, AS minus AN, and then you can write down it. We have shown that the curl of this thing is 0, so we can write down as a gradient of pi, and then this thing is you are in some sense integrating from over the phi from 0 to 2 pi. So the answer will be chi at 0 and chi at 2 pi. Final value chi at 2 pi minus chi at 0. We know the chi, and you can calculate mu naught K1. So we have the magnetic field, which is a combination of these two things, and you can get your Gauss theorem correct. So, but this thing is implying actually. So this thing is actually the definition of this graph string, where this your vector potential is singular, and you can have it at any direction, not just z and minus z, and you can have it can follow any arbitrary path, and you can get one path to another path through gauge transformation, just like we got this vector potential or this cosmic string is connected with the cosmic string going downward with the gauge transformation. So gauge transformation, you can move it around. So something which is depending on gauge transformation is not physical. Physics should be independent of gauge transformation. So cosmic string is a kind of an artifact which should not be observed. That's the key which will lead to charge quantization. So yes, the Dirac string can be moved to arbitrary path. So Dirac quantization, how do we understand? So let's say the quantization of the motion of particle of mass m and charge e in the field of magnetic pole. So you have Schrodinger equation in the presence of electromagnetic field. We know we can write down this, and this is invariant under A goes to this is the gauge transformation. We know the gauge transformation of potentials, and also under this gauge transformation your wave function will form like this. And in covariant form you can relate everything like this. So Dirac string we know is unobservable, should be unobservable. So this put that the Dirac string does not give rise to Aronoff effect. Aronoff effect, what is? So this is a quantum mechanical interference with charged particle in the region with B non-zero, but A B is 0 but A non-zero. So we know the B is 0 everywhere but A is not. Same situation. So consider a charged particle go into state experiment and you consider two pathways. So this condition for absence of Aharonov Bohm effect tells you that the physics should be invariant whether you take this one or this one, and then you can combine these two pathways, it will become a closed loop, and this invariance means this phase should be quantized to n pi. Then this phase factor will vanish, and this will be charge quantization. But I don't understand, so I will speed up. So this was the Dirac monopole. This is singular. This is singular monopole. Now I will talk about another kind of monopole, which are usually called topological monopoles, and it will be related to models like grand unified models or electroweak unification models. And there, let's consider this first one, where two and Polyakov in separate papers showed that magnetic monopoles are generic feature of grand unified theories. What are grand unified theories? These theories try to unify the electroweak with a strong force. So here you can see they have considered a model which doesn't work, but you can call it a toy model proposed by Georgi and Glashow. This is based on SO3. SO3 is isomorphic to SO2. SO3 is a rotation, special orthogonal group, rotation group in free space, and this is isomorphic to SU2. So they tried, Glashow and Georgi Glashow tried to unify electroweak unification, electromagnetism with weak force in SU2, simple group SU2. So there was no neutral current. The prediction of this model is no neutral current, but we have seen that there is neutral current. So this is a toy model. But so they have considered two models in their paper. Slam-Weinberg model. At that time, people call it Slam-Weinberg, but no Glashow. Glashow is this. Glashow model is this. So electroweak unification model, but they know that there is no monopole in electroweak unification. Slam-Weinberg model. So they considered Glashow model. And Glashow model, this part is a bit involved, so I will skip the details. So only done for electroweak unification in SU2. So this SU2 breaks into human electromagnetism. So this way the bosonic sector contains 3 gauge fields. There are 3 gauge fields and 3 component Higgs field. They also consider a triplet for Higgs. And the third component of this W3 they identified with the electromagnetic field. Try to identify with the, and others two are W plus W minus. W minus, W plus and photon. There is no Z. So in contrast to SU2 plus U1, we have additional U1 gate boson, which is B, which B mixes with W3 and gives you Z and photon. So this is the scalar triplet they use and break SU2 to U1. When you use the adjoint representation of SUN, then it preserves the rank in breaking. So the rank of SU2 or SUN is n minus 1. SU2 rank of SU2 is 1 and U1 is also 1. It will preserve the rank. So then they try to find some, they solve the differential equation of this Higgs field, and they try to find some solution which are independent of time, finite energy solution. So these are some solitonic solutions. So they found, and they have spherical symmetry, so that it looks like this monopole. So they found one, and this is they calculated the mass of these monopoles, which is mw over alpha. Alpha is coupling involved. Mw is W mass. And here you see in this monopole you know the mass of the monopole. In Dirac monopole you don't know the mass. Mass is undefined. So, and also the charge. There is some fundamental unit of direct charge, so this is the 2 unit of charge. So now I consider standard model. Do we have monopole standard model? So standard model SU3 cross S2 cross U1. So there is a left, something left. So there is a handedness. So standard model is chiral. Chiral means handedness. It does not treat left and right on equal footing. So this is the projection operator you can apply on the rock spinner. You can obtain left or right. So there are quarks. Quarks comes in doublet, left-handed quarks comes in doublet. So this 2 means it transforms as a doublet. 3 means 3 colors, and the right-handed part is singlet under SU2. Right-handed part doesn't have anything to do with SU2. So this, otherwise it has color, 3 color, 3 color. Left arms don't carry any color, so 1, 1, 1. And left arms, left-handedness doublet and right-handedness singlet. You can also add right-handed neutrino, which is not the part of standard model. But so in terms of chiral, there are chiral degrees of freedom. There are 15 plus 1 for right-handed neutrino. So Higgs is a doublet. And you can see the Higgs mechanism. And there are gauge boson. There are 8 colors, 3 W boson, 1 B boson. And then you have electroweak symmetry gating. You get KUCD, which is unbroken at parallel energies, and you have electromagnetism, and this weak force separated as an intermediate vector boson carrier or 4 fermion carrier, where W's get masses and Z get masses. So weak interaction are mediated by this. When gauge boson get masses, so there is no gauge symmetry, or gauge symmetry is in the broken phase. So next we move on to Nambu. Nambu considers Islam model. He tried to find something in these, see, Weinberg Islam theory. There is no glacier. So, things like configuration in 1977, 2 years I think before the Nobel Prize was awarded to 3 people, 1977. And 1972 to prove the that this model is free from divergences. After 1972, there was news that neutral currents has been discovered, but I think in 1976 or later they have announced it properly. Slam Weinberg. No one knows about glacier. So this is the Weinberg slam. Note that the standard model does not contain topological sphere. So what does he found? He found a kind of composite thing. Monopole, anti-monopole, and they are connected by Z strings, and this is an unstable configuration. They go away quickly. So now little motivation for the grand unified scheme. So we have lot of parameters in the standard model, and we try to reduce it. We try to make connection among these parameters, and in the grand unified case you can have these connections. So there are masses which are represented by Yukawa coupling, gauge coupling. You have 3 gauge couplings and things like that. You have 19 plus free parameter. So grand unified theories unify gauge couplings and also Yukawa coupling. If you add supersymmetry, it connects the boson with fermions, so Yukawa and quartic coupling gets connected. So this is the situation in standard model, no gauge coupling unification. If you add SUSY, you have unification, and the lightest particle can be treated as this. So I will describe this SU5 model and Patislam model. SU5 model, you can combine different multiplets like down type and lepton type multiplets into 5-plet, and this quad and this right-handed up and electron into 10-plet. So 5 plus 10, 15. You can put all the standard model stuff into 2 multiplets. And if you can also add right-hand neutrino, but this model does not require it. If you want to add just like standard model. But in Patislam model, this was the first unification model. You have 4 to 1. So it says that we can see leptons as the 4th color of quad. So title is lepton number as a 4th color. So you have 4 to 1, 4 to the 8, 4 to the 8. We have 16. So there are 2 multiplets, 4 to 1, 4 bar 2. So you have 8 plus 8, 16. And this model requires right-handed neutrino should be there. The presence of right-handed neutrino can explain the tiny non-zero masses of neutrinos which have been observed. So this is the motivation. And as of time we have only one multiplier, 16, everything, all matter stuff in one representation with right-handed neutrino. Charge quantization, we can rephrase the charge quantization in terms of why proton charge is related to electron charge. So proton charge is plus 1, electron minus 1, neutron this. So charge quantization. In grand unified theories, there are generators which generate this gauge transformation, and all these generators are traceless. So we consider the generators which are diagonal, and we try to make the charge operator from that generators. So because this charge operator, this electromagnetic charge operator is coming from the generators of grand unified theories. So, and the generators of grand unified theories are traceless, then this charge will also be traceless. So when you operate this charge operator on a fundamental representation, let's say SU5, कि आप 5 representation पे इसको operate करते हो, so there are 3 down type quarks, 1 positron and 1 neutrino. You know the charge of neutrino is 0. So the charge of down quark is related to this positron. And you can also, because in proton you also have up type quark, you can also, as an exercise, you can also apply the same thing on tanglet. Tanglet, you have up and down quarks. There the quarks of up and down are connected. Then you can get this result. You can explain that why proton charge is minus times the charge of electron. So this is the charge condition. This is built in. So in grand unified theories, you have charge quantization. You have charge quantization, and I have developed a connection between charge quantization and the existence of monopole. Drag says, you give me the monopole, I will explain the charge quantization. Grand unified theory is built in explaining the charge quantization, built in. So it is predicting monopoles. So monopoles, magnetic monopoles are generic prediction of grand unified theories.
Independent alert in SU5.
SU5, n square minus 1, 24. Okay, so these monopoles are not point-like, it has a size, and its size is related to the symmetry breaking scale. So this is a picture where you can see it has a core. This monopole in SU5 monopole has a core. And the technical language for topological defects is this pi maps. So if the pi map or symmetry is broken, there is a vacuum manifold. If that vacuum manifold, the pi map of that vacuum manifold is non-trivial, then you get a monopole. Simply, in simple words, if you connect the 2 points, if you can connect if you cannot connect the 2 points, there is something in between, then there is a domain bond. So if you contract a loop to a point, if you cannot contract a loop to a point, then there will be a cosmic string. And the same goes with if you have a sphere. If you cannot sphere, the topology of vacuum manifold is such that if you cannot contract the sphere, then there will be a monopole. You can generalize this idea in simple words. So these monopoles, the gut monopoles are heavy, very heavy, and it can disturb the Big Bang nucleosynthesis because it predicts the density very high. We know this omega parameter is around 1. Currently the omega parameter is around 1, but it predicts 10 to the 11th. But so this was the problem which Alan Guth was working on during his PhD in the MIT. And then he saw, if in some way I can dilute this density, then we are okay. And then he saw that this dilution, the expansion, huge expansion, can also solve some other problems, horizon and flatness problem. So do we have electroweak monopoles? Electroweak monopoles are some kind of monopoles which carry electroweak charge. So I will just mention you the monopoles which are not so much heavy, which can be tested at future colliders, low energy colliders. So electroweak monopoles, magnetic dumbbells. So this is a paper by George Lewis and Kassel Shafi. So they try to see if we can have electroweak monopoles in this paper and this paper. So they kind of propose a composite monopole, Dirac plus Nambu monopole. This is the shape. So this one is SU2 left, Nambu monopole. So in Nambu monopoles you have SU2 left, or you have this one is U1 by monopole, is a Dirac monopole. So this is a composite monopole. And how did they get this monopole? They introduce a Higgs triplet. So they introduce a Higgs triplet, and which is related with the so apart from the doublet Higgs of standard model, they also have triplet. So once your doublet Higgs gets away, that Higgs also gets away, and that triplet Higgs actually reserves the rank. So it breaks the SU2 left into U1 left. So SU2 left into U1 left, we have a monopole here, and then U1 left and U1 Y breaks down from doublet Higgs. So they kind of delayed this breaking in some way. So this the triplet gets away, and they managed to get from electroweak Precyon data they put a bound on this mass of this triplet about 4.4 tab, which will be accessible in LHC and others. So this triplet with mass and tab scale could be our new source for Higgs production height. So this triplet you can get from GURTS in 24th presentation. In 24th presentation in issue 5 you have this triplet. So monopoles are well motivated new particles that exist in GURTS and also in string theory and can explain charge quantization. And heavy GURTS, I mean, you have to dilute those heavy GURTS because it's not consistent with the Big Bang nucleosynthesis and observation. So it can be done by inflation. I have not talked about intermediate scale monopoles. They can have testable prediction around 10 to the 11 Jav or so. And then there are people have also talked about tab scale monopoles, and which can be detectable in medal or future colliders. So detection of monopoles will open up a new window to link it to the new physics beyond standard model. Thank you.